Hi, Farouk here at DirectUp. I hope you're having a good day so far and you're pushing through your FE exam prep at a pace that's just right for you. So today we're going to get some practice in. It's actually a very good practice problem covering activated sludge and that wastewater treatment. So this is a good one to go through and it's a relevant FE type question. Before doing this practice question, I just wanted to let you know my Civil FE review course is currently 20% off for the rest of November. So you can use the link below to get 20% off any plan you choose for my Civil FE review course. So now you might be asking, is this right for me? Why should I invest in a Civil FE review course? So first of all, this is designed for those that simply don't have the time to put in when you're trying to gather all the right resources, gather the right practice questions, and also learn the right skills and problem solving for something like the 2022 FE exam. This exam is changing, therefore you need updated resources, relevant conceptual knowledge, and all of that, and the right problem solving skills and mindset for something like the FE. And this course will do just that. It's gonna guide you step by step. You're gonna go through these sections, one section at a time, one practice problem at a time. You're going to learn the right problem solving skills. You're going to learn the right tricks, calculator tricks, all of that. You want to ensure you're prepared as best as possible. And I can guarantee that this course will absolutely do that. Now let's get into the fun stuff. So you know the drill. Pause the video, write what you're given, what you want to find, and do your best to arrive at a solution. It's okay if you get stuck. It's okay if you make mistakes. Because I know when I did this the first time, I did make a mistake. Now I've learned from that and I'm going to redo it with you to show you these right steps to arrive at that final answer. So please pause the video, struggle through it. It's okay if you get stuck. This is not an easy one and it can be a little tricky, especially for activated sludge and wastewater treatment. Okay, let's read this problem statement. We're told a wastewater treatment plant has an effluent flow rate of 2 mgd, million gallon per day. So in the US, this is the units. Like for wastewater treatment, we have these usually in million gallon per day. Those are the common units. The primary sludge contains 30,000 milligram per liter of suspended solids. The aeration tank has a MLSS, mixed liquor suspended solids concentration of 3,500 milligram per liter, and the recycled sludge flow rate from the secondary clarifier is 0.9 mgd, containing 9,000 milligram per liter suspended solids. So that's a long sentence there. This is saying MLSS is this concentration, and the recycled sludge flow rate, we know we always recycle that sludge, that has this flow rate, Q recycled, is 0.9 mgd, but it has a concentration of 9,000 milligram per liter. And we'll denote that on a diagram as well. The effluent suspended solids concentration is 20 milligram per liter. So the effluent is like what comes out after secondary treatment at the in the final stages of the treatment train. So we're told the waste sludge flow rate in mgd is most nearly what? So first, let me denote what I want to find. I want to find the waste sludge flow rate, and we can denote it as QW, and that's how it's denoted in the handbook. And let me write it as QW, and we want units in mgd. So we know in this case everything will be mgd, so we don't really have to worry about the units. But what I'll show us at the end is how to convert it to gallons per day, because right now it's million gallon per day. So this is what we want to find, and what we can do next is actually begin denoting what we're given. So let's draw what we're given, and what we can do first is actually draw the system, draw this overall treatment. And the most important part in this case is that biological treatment, which we call secondary treatment. That's where we're going to focus on in this one, especially because they ask us to find QW. We know QW occurs in secondary treatment where we have the aeration tank and the secondary clarifier. Secondary treatment is that system. So what I can do first is actually denote my primary clarifier. So in this case, I'll just use a circle and call it the primary. primary, and you can think of it as the primary sedimentation basin. So what comes after primary? The aeration tank. So we'll put the aeration tank right after that, and I can denote it like this, and we know this is going to be my aeration tank, and this will always have a volume as well. So aeration tank. And after the aeration tank, what comes? Secondary. It's the secondary clarifier, which is like a secondary sedimentation basin. So just note, clarifier means sedimentation basin. Same thing. So now, this will be my secondary, and I'll denote it as a circle as well. And I'll call it secondary. Now let's start putting the numbers that were given on our diagram. So first of all, we're told a wastewater treatment plant has an influent flow rate of 2 mgd. I'm going to put that as what comes into the plant. So we know it comes in, we have the grit chambers, we have the screens grit chamber, maybe an equalization basin. Then we have that primary, but that flow is just going to stay at 2 mgd when it enters the primary. So it's 2 mgd. So I want to note the primary actually does have some sludge that comes out at the bottom. It's like a sedimentation basin, and we have some settling, and at the bottom we do have some sludge that comes out. So what I can denote and be accurate here is, say we do have some sludge that's wasted from that primary, and it does come out at a flow rate, but that flow rate is usually so small that the 2 mgd will come in and come out. So we're not going to really apply a mass balance around that primary to get what comes out in terms of the flow rate. We're going to say that 2 mgd of that comes into the whole wastewater plant is what is going to be coming in and coming out the primary. So in this case, we can denote it coming out like this. Then it goes into the aeration tank, and I can put 2 mgd here for that. So then what else are we given? We're told the primary sludge contains 30,000 milligram per liter of suspended solids. So we will say, okay, this will have a suspended solids of 30,000 milligram per liter. But we will see this is actually not relevant and not important to solve this practice question. It may be if we were trying to find the total sludge that's wasted for the primary and secondary. Maybe that's a question. But in this one, it's not going to be relevant and it's not important to solve the question. So then we're told the aeration tank has a MLSS concentration of 3,500 milligram per liter. So I can denote that as X or XA. I'm going to stick with the FE handbook and call it XA. And no, MLSS is always in the aeration tank. So that's going to be 3,500. So we call that in milligram per liter, mixed liquor suspended solids. So if you see X or XA, usually it's that. It will be that in the aeration tank. So from there, we're told the recycled sludge flow rate is 0.9. So now we want to note that this comes in and we have some flow that comes out. And we know from the secondary, we do recycle some flow and it goes back. And we will go in here. We're recycling this. So this will have a QR value. And that QR will be the 0.9 mgd. So that's that, and that's what's given. And it contains 9,000 milligram per liter. So when they say 9,000, they're referring to the XR. It's the suspended solid concentration, 9,000 milligram per liter. So that is denoted. Then we can keep going. It says the effluent suspended solids is 20 milligram per liter. That's what comes out the secondary. So we will say effluent is always at the very end after secondary. And we denote that as, so the concentration is going to be X. So we can denote that as X effluent, E for effluent, as 20 milligram per liter. And then we want to find Q waste in mgd. So now my question for you is, where's Q waste? Q waste is going to get wasted from the secondary. Yes, we do waste from the primary, but usually what we're focused on for that secondary treatment for something like the FE is that QW, which is going to be this. We can show it like this. QW is the question here. And when you have a QW, we do have a XW. XW, which is the suspended solid concentration of the wasted sludge. So now, what is that going to be? We can get that. We know it gets recycled at XR. Would you agree with me that XR is XW? It is. It's the same concentration. So XW is actually XR. So it should be 9,000. Even though that's not stated, that's something we have to know. Milligram per liter. So XW is always going to be the same as XR. And from there, we can break this down a little bit more. But before that, I just want to introduce the FE handbook just to expose us to that. So if I go in the handbook, I can do the Control-Shift-F and type, in this case, activated sludge. Or you can type activated. And it's going to give you that page. And that's going to be the most important section. And what we will focus on in this case is actually going to be the value for this steady state mass balance. So we're going to apply this equation to solve this question. So I brought in the equation for us, and we know we're going to apply this around a mass balance for the secondary clarifier. So what they're doing here is essentially looking at a mass balance around this part, which is actually what we need. This is what we need to find QW. It's a mass balance. Think of a control volume around that secondary clarifier is what they're showing. It's not the whole treatment train. That's different. So we can have a control volume about this. That's different. A control volume about this. This one shows a control volume about the secondary clarifier. So now we know that this Q naught plus QR is something we did not denote here. So this is actually what comes in to secondary treatment. This whole process here is secondary treatment. Q naught plus QR will be the QR that gets recycled, then it comes in to the whole secondary treatment. And that Q naught and QR is what comes out the aeration tank. So what I can do for us, I want to be careful here. Let me put this point here. Then what happens right after that point is we have the Q naught plus QR. And this Q naught plus QR is going to be this Q naught. This is actually our Q naught. And think of that as the effluent out of the primary tank, which is the influent into the aeration tank and overall secondary treatment. So that's going to be the Q naught. This is Q naught. So then we go back, we can apply continuity, or like what comes in has to come out around this point. And then what comes out here will be Q naught plus QR into this whole portion. So that's Q naught plus QR. And this same Q naught plus QR goes into the aeration tank and it has to come out. So it's actually the same as this Q naught plus QR that comes out the tank. And that Q naught plus QR will have a concentration. They denote that as XA. It's the concentration MLSS from the tank. So it brings with it that concentration XA from the tank. That goes into the secondary. Then we know on the right side, it shows what comes out. It shows QE, XE. So this is our XE that comes out, which has a corresponding QE. And we'll look into that. Then we have QR. So QR comes out. And no, it's going to be this one. And we have XR at this concentration, suspended solids. Then we have QW, which is what we want to find. Then we have XW that comes out the secondary. Now let's start plugging stuff in. So we know what comes out the primary goes into the secondary treatment, which is going to be Q naught. It's the 2 mgd. So we put that for the Q naught. So we put 2 mgd. And then we add QR. We're adding QR because, no, this is around, again, the secondary. So we have to add QR. Q naught plus QR is what comes in. So we add that, and that would be the 0.9 as given in mgd, million gallon per day. Then we multiply that by XA, which is the MLSS, which is 3,500 in milligram per liter. Then we take that equal to, so this side is what comes in. What comes out is going to be the QE, XE, QW, XW, QR, XR, and that's what's denoted. So we know QE is going to be a value that we do not have. So let me keep it there. We can get that though. Then we would do XE is going to be 20. That's given. Milligram per liter. Then we take that time plus QR, which is 0.9. And that would be MGD. Everything in this case is MGD, milligram per liter. So that's QR. Then we do XR is going to be the 9,000 milligram per liter. Then we do plus the QW is going to be actually what we want to find. We don't know that. That's the goal to find. Then XW is going to be 9,000 milligram per liter. As we said, always XW is the same as XR. So now the problem we face is we have one equation, two unknowns. So we can't really do much with it. But there's something we can do. We can actually isolate that secondary clarifier. Let me denote this for us. This is the secondary. And if we look very close at this, we know we have something that comes out, QE. I'll just focus on the flow rates. And something that comes in, which will be the Q0 plus QR, as we denote it here in the secondary. Then we know stuff comes out of it down as well. So we have the QR that gets recycled, and we do have the QW as well. So these are separate. We cannot combine these. So now from this, what I'm going to show you is do a mass balance, or in this case, continuity about the secondary in terms of flow rate. So we can say whatever comes in has to come out. What comes in? What comes in is Q0 plus QR. This comes in, right? Then what comes out is everything else. It's QE. Let me denote that. It's going to be QR and QW plus QR plus QW. And notice what happens with QR. They cancel. They're the same on both sides of the equation, equal sign. They would cancel. And that makes sense logically because it comes in and it's just going to be recycled. It's not like a flow rate that actually gets wasted like this. It's going to come in and just go in a loop. That actually cancels. It doesn't do anything really for that secondary clarifier. We do recycle it into the aeration tank though to give it that activated sludge or that fresh sludge in that aeration tank. But we know that actually cancels when we look at this. So QR cancels. Then we have Q0 is going to equal to this. So Q0 equals to QE plus QW. And now we can isolate QE to get Q0 minus QW. And why we did this is now we can take that QE here and put it in here. And doing just that, we can start simplifying this. So let me simplify this portion first. So do the math with me. So we can take 2 plus 0.9 times 3,500. So we get 101.50. That equals to, so we know QE is going to be this part. So we did that and got that from a mass balance around a continuity balance around the secondary. So that would be Q0 minus QW. And that is multiplied by the 20, which is going to be this portion. Then we do plus 0.9 times the 9,000. We get 8,100 for that one. Then plus QW times the 9,000. So that will just keep it like that. So now notice we have, at this point, we can actually plug in the Q0. So that Q0 would be what comes in, right? It says it's 2 and we denoted that as 2 MGD. So we just put 2 MGD for that one. And we can reduce this so it's going to be 101.50. So we put the 2 minus QW is what we want to find. Remember, that's the goal. Times 20 plus 8,100 plus, we can put the 9,000 in front just to make it look nice, times QW. And now look at this. You have one equation, one unknown. We can find QW. So what you can do here is basically distribute the 20 and distribute the 20 to the 2. Do that algebra, then combine like terms. It's going to be basic algebra. It's a skill we have to learn for the FE, and I do teach that in depth in the course, but it's just doing that algebra and really solving for QW. And when we solve for that QW, what answer are we going to get? We should get close to 0.224. 0.224. And that would actually be in what units? Units of MGD. Just note, when you're doing for the US, I know we can, in SI it's a little different. In the US, and for something like the FE, it's usually like working with treatment trains or wastewater in MGD, milligram per liter, or pound per day. We look at the sludge coming in units of pound per day. Those are the units. So if we have MGD there in all of our flow rates, we're going to get an output of MGD, million gallon per day. So in this case, the unit should be million gallon per day. So our answer would be this. And if you wanted to get this in gallon per day, all you do is multiply by a million, or 10 to the power of 6. You can get it in gallon per day to cancel that million term, which is 10 to the power of 6. But in this case, the correct answer would be C. I hope you found this helpful. Please, if you have questions about this activated sludge process or any questions about the FE, just let me know in the comments below. Keep up the good work, and I'll see you in the next video.